Sorry, go ahead. Okay, thanks very much for the introduction, and I'm really pleased to be able to speak in this conference. So thank you to all the organizers, and thanks to everybody for coming to my talk today. I'm going to discuss a specific class of solutions to the Painlevé-III equation in what's called the D7 degeneration. And this is all joint work that I'm going to explain with Robbie Buckingham at the University of Cincinnati. Okay. So just to start out, here on this slide is this is my slide of all of the Painlevé equations. Okay, so P1 through P6, and all of them except for the one that's in gray. That's the Painlevé-I equation. All of them except that have one or more free constants in the equations, and they're indicated with the blue color. So Painlevé-II has just the constant alpha, and Painlevé-III has four constants, alpha, beta, gamma, delta, and so on in the equation. Okay. Now, in general, what's great about the Painlevé equations is that they're defining for us some modern special functions, highly transcendental functions. But although that's the typical situation, all of the equations except for the Painlevé-I equation, they admit, at least for special values of the constants in the equation, they admit solutions that you can express explicitly in terms of either elementary functions or perhaps classical linear special functions like Airy functions, Bessel functions, and so on. And when we think about the values of these constants in the equations for which the special function solutions will exist for a given equation, these parameter values are related by some finitely generated group action, something like a lattice, something like that. And at the same time that the parameters are shifted around by the action of this group, the group acts on the solutions themselves via Becklin transformations. And the thing about the Becklin transformations is they have the property that they're preserving the character of the solution. So if the solutions are rational and we act with the Becklin transformation, we return, again, a rational function. So that's the basic idea of the special parameter values and special solutions of these equations. Now, it goes way back to the beginning with these equations. Richard Fuchs and Garnier, of course, noted that every single Painlevé equation defines an isomonodromic deformation of some second-order linear differential equation. And it's now, of course, become common and useful for us to think in terms of first-order systems instead of second-order linear equations. And so in this case, we come to the notion of a lax pair for a Painlevé equation. That is to say that every one of these 6 equations on the first slide can be represented as the compatibility condition for 2 of these first-order linear equations on some auxiliary unknown that we may take to be a 2x2 matrix capital psi. Okay. Now, for such a lax pair, we may consider the inverse problem. That's the problem of constructing the simultaneous solution of say the differential equation with respect to the spectral parameter from the monodromy data of the problem, which of course is invariant under the second equation, the one that's the deformation, the isomonodromic deformation. So that inverse problem can be formulated, say, in the complex plane as a Riemann-Hilbert problem, and when we think about what's happening now in terms of these symmetries that move the parameters around and also change the solutions by Becklin transformations, how does that act on the Riemann-Hilbert problem? Well, it's really acting on this matrix, this fundamental matrix psi, as a gauge transformation, a linear gauge transformation, and in this setting they're called Schlesinger transformations. So these Schlesinger transformations, they don't affect the monodromy data, but what they do is they just change some formal exponents in the Riemann-Hilbert problem at certain singular points. And the way that these exponents are important for us is that they are encoding the special parameter values where we have, say, an algebraic solution, a rational solution of the Painlevé equation. Okay. So what it means for us is that the Riemann-Hilbert representation for this entire family of special solutions that are transported around by the symmetry group, this whole family can be found, or the representation of every solution in the family can be found explicitly once we know how to do it for just one of the solutions in the family. And that sometimes we pick the simplest. We usually pick the simplest solution. That's called the seed solution, and it's the one that generates the whole family, the seed solution. So the difficulty with using this kind of isomonodromic approach to Painlevé equations is that in general the monodromy data for a given solution is really a dream to obtain in concrete form. So we usually cannot obtain the monodromy data explicitly. But what I'll show you, and what seems true in many examples, is that for these elementary function seed solutions, at least the direct problem for the lax pair, that is to say, construct the monodromy data for the solution, that can frequently be solved in terms of classical special functions. So we can build the fundamental matrix psi out of classical special functions when we're talking about the special solutions, like rational solutions of the Painlevé equation. And then once we have psi, we can compute the monodromy data explicitly as well, because those classical special functions enjoy connection formulae that are known, and we use those to generate the jumps that connect the different solutions that are normalized in different sectors. Okay, so that's how we can get the Stokes data, for example. So at that point, what we can do is we can use the Riemann-Hilbert representation of this whole family of solutions that are obtained by applying the Schlesinger transformations to the Riemann-Hilbert problem for the seed to deduce all kinds of useful information about the special solutions. And this statement is especially relevant when we consider extreme values of the parameters. So remember, we have this group action that's moving the parameter values around, and as such, we can make the parameter values very large, and then we're talking about like an asymptotic analysis problem in Riemann-Hilbert theory. So we may use these Dave-Joe steepest descent techniques that Marco mentioned in his talk. And we can learn some information that's useful and interesting about these solutions. Okay, so what I've just kind of summarized here on a couple slides is what we might call the Iso Monodrome method for these solutions, and it's been successfully applied in the case of rational solutions in several settings. I'll just outline a couple. So if we think about the second Painlevé equation, so then there's this one parameter alpha, and whenever alpha is an integer, there is a rational solution that's unique. That's an if and only if. So that's the family in that case. It's parameterized by integers alpha. And in this setting, if you look at the Jimbo-Miwa lax pair for the Painlevé-II equation, and you plug in the seed solution, which is just the zero function actually, then you find out that that's solved explicitly in terms of Airy functions. So the lax pair can be solved explicitly in this sort of Painlevé-II case, and here your friend is the Airy function. The Painlevé-III equation, if we consider what's not really the topic of this talk, the main topic, but we consider the more generic form of Painlevé-III, that's called the D6 type equation. That one admits rational solutions parameterized by, well, an integer comes up, and there's also just a complex parameter that's free. And if we take the seed solution for this family, I'll, by the way, tell you some more details about these later, but if we take the seed solution for this family, then we find out that the Jimbo-Miwa lax pair for Painlevé-III is solved by mapping it really to a confluent hypergeometric equation. So Whittaker functions can be used to solve for psi, and then you can use connection formulas for Whittaker functions to find out how to write the Riemann-Hilbert problem for all of the rational solutions of Painlevé-III. And then for the Painlevé-IV equation, what's interesting perhaps is that there are two distinct families of rational solutions, and each of them gets parameterized by a pair of integers. So there's two kinds. There's the so-called generalized Hermite rational solutions and the generalized Okamoto rational solutions. And in each case, the lax pair can be solved explicitly in special functions. Actually, for the generalized Hermite case, it's really elementary functions that you can use to solve the problem. But for generalized Okamoto, it's Airy functions, just like it was for Painlevé-III, actually. Okay, so so now let me start talking about the D7 degeneration of Painlevé-III and what we can say about it, what we know about it. So here's the D7 degeneration. What happens, remember, perhaps the Painlevé-III equation has 4 parameters in general: alpha, beta, gamma, delta. And if gamma is 0, then that's called the D7 degeneration. And here, to prevent further degeneracy, we assume that alpha delta product is different from 0. So this is the D7 equation. And this one does not have any rational solutions, actually, for any values of the parameters. However, if alpha is a positive number and beta is twice an integer, delta is -1, then it has a unique algebraic solution. So we'll call that u sub n, corresponding to this value of the integer n in beta, u sub n of x. And what it is it's a rational function of the quantity x to the power 1/3. So if we scale the coordinate x and the value of the function u by a constant c, that leaves beta and delta alone, but it does scale the alpha. So that means we can really change the alpha to any number that we like, and without loss of generality, we're going to take alpha equals 8, in which case the seed solution for the family, the one that has index 0, is exactly 1/2 times x to the 3rd. And more generally, for this family, if we allow the index n now to vary, what we can tell from looking at some representations that I'll describe later of the solutions is that each one of these things for large x kind of looks the same. They all look like 1/2 times x to the 3rd when x goes to infinity. That's true for each fixed value of n. Okay. So, well, since this u sub n function is a rational function of the quantity x to the 1/3, capital Z, we'll call that capital Z, it can be represented, of course, as a ratio of polynomials. And here, it turns out that the right way to do it is to use what are called the Oyama polynomials. So P0, P1, and so on. And these are defined by some initial conditions. P0 is the constant function 1. P1 is the function 3z squared, and then we have a recurrence relation here. And the thing about this recurrence relation is that it requires division by Pn minus 1 of z. So really, it's a recurrence relation a priori, right? It's a recurrence relation on rational functions. However, it turns out that this Pn minus 1 of z is always a factor of the right-hand side. And so consequently, Pn plus 1 of z is a polynomial. There's another factor of z here, I forgot to say. You should divide by that too. Okay, so with that fact, we can represent the un function as a ratio of Oyama polynomials in such a way. So we put Pn plus 1 and Pn minus 1 in the numerator and a constant times Pn squared in the denominator. So I guess this means that that all of these functions actually have double poles. That's what it means because of the factor 2 here. Okay. So once you have the recurrence, of course, it's very nice to make plots of the zeros. Those are going to be the poles ultimately, and the zeros of the algebraic solutions. And it's convenient to plot them in the z-plane. Z is x to the 1/3. So here are the roots of P5, P10, and P20, and they form obviously the shape of a bow tie. I forgot to put on a bow tie today, but now you see it on the slide. So that's what it looks like. And these sorts of plots were pointed out in a paper of Peter Clarkson from 2003. But anyway, the fact is that this bow tie shape is somehow becoming better and better defined, I would say, as the index n increases. So it's somehow the bow tie is a phenomenon that should be explained. And it clearly, from these plots anyway, it's got something to do with the limit as n goes to infinity. So that's really the problem that we would like to somehow think about, is what happens to these algebraic D7 solutions when the n parameter is going to infinity. Okay, so here's the D7 equation again. And I wrote it with this delta being -1, the beta is 2n, and alpha is 8, the way that we said we would write it. So when n is large in this equation, it sort of is begging to be treated formally anyway by some kind of dominant balance argument. So you can kind of look at the equation and figure out when n is large, how should the u scale? How should the x scale to achieve some dominant balance? And the right scaling is that u should be proportional to the square root of n. So we'll call little u n to the half times capital U. And then also that the x variable should scale like n to the 3/2 times something else. We'll call it y. It's also useful to perturb a little bit. So we'll add in 1 over n times z. And the way we regard this kind of transformation really is that this is a relationship between x and a new independent variable z that's parameterized by a constant number that's different from 0. That's just this number y right here. So this is a parameter. X and z are going to be the independent variables, and it's just a change of variables. Okay, so then you write down what's the differential equation for capital U as a function of small z here. And one gets this differential equation like this. And there's a small term, a formally small term. It's got a 1 over n in front. So if we drop this formally small term, then what we're looking at is a second order autonomous differential equation for the function capital U of z, but it involves this parameter y, which is some non-zero constant. Okay, that's the approximating equation. It's a formal observation. So, okay, well, here's the approximating equation, and there are two types of solutions that are easy to see for this problem. The first one consists of just functions u that are constants. They're independent of z, so all these derivatives are 0, and these are obviously just by clearing out the denominator, they're roots of the cubic equation 8u cubed plus 2u minus y equals 0. So this y is a constant. But anyway, it's also, of course, some scaling of the x variable. So we may think of them as slowly varying functions somehow. So when y goes to infinity, this capital U, of course, for this cubic equation should look like 1/2 y to the 1/3, or obviously there's other cube roots. So we can put in those factors e to the plus or minus 2 pi I over 3 as well. And back in the original variables, back when we go back to x, we have the little u is basically 1/2 times x to the 3rd plus higher order corrections as x goes to infinity, which of course matches what we know to be true about this un function of x. For each fixed n, it looks like 1/2 x to the 1/3 as x goes to infinity. Anyway, so that's again some kind of formal observation, but these are the equilibrium solutions. And then for non-equilibrium solutions, we could multiply through by this non-zero quantity u prime over u squared and integrate the equation once. So some integration constant e shows up, and we have a first order second degree equation like that, which is really just the Weierstrass equation. Okay, so here the invariants G2 and G3 are written in terms of the original integration constant e that showed up right here, and then this parameter y that was in the equation. Oops, I'm sorry. Okay, that's over here. Yep. Oh, and it's not exactly just Weierstrass and u. I have to sort of make a linear transformation like this to the squiggle function. Okay. So based on this kind of formal argument, I guess, it's reasonable to expect that the un function, this algebraic solution of the D7 equation, it could perhaps be modeled by an equilibrium solution for large x and by some kind of modulated Weierstrass function where the invariants are functions of some slow variable for smaller values of x. That seems reasonable. It also matches the pictures. But you know, the formal scaling arguments are not at all rigorous, of course, and some proofs are going to be required. And it's also, I have to say, even if that's not your concern, it's not at all clear from what we just discussed where or why one type of approximation should somehow give way to the other in the complex plane of the original independent variable x. You know, why should we switch from elliptic behavior, Weierstrass behavior, to something that's like constant equilibrium behavior? So anyway, so to deal with both of these problems here, what we can do is apply the Iso Monodrome method to obtain a kind of a Riemann-Hilbert representation of these algebraic solutions un of x, using this idea that we mentioned at the beginning, that we sort of summarized at the beginning. And then once we have that Riemann-Hilbert representation, we could apply the Dave-Joe steepest descent method and consequently be able to rigorously address this limit n goes to infinity, and hence say something about the bow ties, okay? All right. So yeah, so that's going to be that's what I would like to describe. But maybe before I get into that, what I could do is describe for you how this method that we described in some generality at the beginning, how it handles actually just the rational solutions of the D6 version, the non-degenerate version of the Painlevé-III equation. Okay, so without any loss of generality, let's take gamma to be the same as minus delta. Both of them will be 4. And then we can introduce parameters n and m in place of the alpha and the beta. So then the Painlevé-III equation can be written in this form here with parameters n and m showing up, just like that. So this is known to have a rational solution if and only if either n or m is an integer. And if only one of them is an integer, then there's going to be 2 rational solutions. But on the other hand, if both of them are integers, then you get 4 rational solutions. Now, they're all related by some simple symmetries. So it's really good enough just to describe the rational solution. It's really a unique function, unique rational solution. We'll call it un of x with parameter m that has the property that at infinity it's equal to 1. So here n is the integer index, m is just an arbitrary thing which could be an integer, but it doesn't have to be an integer. Okay, now when n is equal to 0, this function is exactly just the function 1, and that is the simplest thing that I can think of. So I'm going to take that to be the seed solution for this family of rational solutions. Okay. So there's a lax pair for the Painlevé-III equation in terms of first order systems. You can read about it in Jimbo and Miwa's paper. I think it's the second paper in the series in the appendix. But anyway, it involves their lax pair involves 4 potentials. Okay, so v, y, s, and t are functions of the independent variable x, and there's a parameter they call theta infinity. It's like a formal monodromy exponent at infinity, but in terms of our parameterization, it's the same thing as m minus n plus 1. Okay, so then the Jimbo-Miwa lax pair is written here on the slide. So this is like the spectral equation in the spectral parameter lambda, and here is the sort of isomonodromic deformation in the variable x. And okay, so it's some pretty simple coefficients at the sort of leading order for large lambda, but here at the bottom end, it looks pretty complicated, okay? The thing to keep in mind about this complicated looking matrix that's the same one in both of these problems here is that it's really just the most general parameterization of a matrix that has the eigenvalues plus or minus 1/2 I times x. So that's basically the same as like this matrix over here. So you could say that what you might think of is that in this case, you've chosen to diagonalize the leading terms at infinity, but you could have decided by some constant gauge transformation to instead diagonalize the terms at 0. Okay, you could do it either way. It really doesn't matter. So they're both coefficients are diagonalizable. The leading terms at infinity and 0 are diagonalizable. That's characteristic of the D6 general version of the Painlevé-III equation. Okay, well, anyway, if you calculate the compatibility condition for these two equations, you get a system of ODEs on V, Y, S, and T. Okay, so that system admits a first integral that's called theta 0, and that's the formal monodromy exponent about the point lambda equals 0. So that's n plus m, and that actually implies then by reducing out by that first integral, it implies the Painlevé-III D6 equation for the quantity u of x, which is just the fraction minus y over s. So that's how we have a Painlevé-III as a compatibility condition for a lax pair. So if we take the parameter n, this integer parameter n here to be 0, and consequently take the solution to be the constant function 1, that's our seed, then the potentials v, y, s, and t, they are really determined up to by this system, by this nonlinear system, up to inessential constants. And they're really quite elementary functions of the variable x. So v of x is some constant times a linear function in x like this. And then here's some exponential part and a power, x to the minus theta infinity. And similarly, expressions for y, s, and t. And I guess all of them involve these exponentials here, right? You see this e to the plus or minus 2x everywhere, and also powers of x to the plus or minus theta infinity. So it sort of suggests that we should maybe simplify things further once we plug these in to the Lax pair equations. But maybe what we could do is simplify further by taking out those factors. So anyway, here is the exponential part coming out, and this part deals exactly with these powers here. When we write theta infinity in terms of m and n, this is how it comes out. And so that means we're making a transformation really from the psi matrix to something called W. And here, this C of lambda is a matrix that can only depend on the spectral parameter lambda. So what I'm doing here is I'm putting this into the X equation. I've underlined this part because that's really the strategy here. The function, this function u equals 1 is very simple as a function of x. And so we have a chance, if we look at the X equation and solve that one first, we have a chance of being able to do that in terms of special functions. And then we can say, okay, by compatibility, it's got to be possible to find a matrix C depending only on lambda, so that I can then put this one in and solve the full system, okay? That's the idea. So anyway, we plug it into the X equation. And as I said, it's useful to take out those exponential and power factors. And then what you wind up with is a matrix equation, a differential equation in X for this function W. And what you discover is that the first row of this matrix W, the elements of the first row, they satisfy the confluent hypergeometric equation. So here, this kappa parameter is 1/2 of m, and the mu parameter is 1/4. And I guess you have to change the independent variable. So instead of x, we have zeta, which is ix times lambda minus 1 over lambda plus 2 times I. So that's what I mean by solving in terms of special functions. Okay, so then you take this formula with the hypergeometric functions, you put it back into the lambda equation, and then you find out that this factor C of lambda has to be a scalar, lambda plus I to the negative 1/2 times an absolute constant matrix C. Okay. So what we want to do now is somehow pick this constant matrix C, or equivalently, work with different fundamental pairs for the confluent hypergeometric equation in order to match normalized solutions at 0 and infinity in different Stokes sectors. So we'll take for the fundamental pair of solutions, we'll choose the Whittaker functions, okay, with argument plus or minus zeta. And those things have branch cuts on the real line for zeta. So the thing about that, of course, is that the real line for zeta, let me just remind you of the formula. The real line for zeta is something in the lambda plane, but it rotates around depending on this on the value of x. That's somehow tied to the fact that the Painlevé-III equation has a singularity at the origin. So what it means is that the jump contour for this problem depends on x in a complicated way, perhaps. Here's the picture when argument of x is pi over 4. You see that this is the image of the real line. These two curves here are the image of the real line for zeta. And this is the picture when arg of x is minus 3 pi over 4. Okay, actually, it's the same picture, but the left and right half lines have reversed their roles, is what's happened. And if I tune continuously arg x between these two, the whole picture has to move in some continuous fashion. So in any case, you see that there's 2 Stokes sectors at infinity. We'll call them omega infinity minus and plus. There are also 2 Stokes sectors at 0. And then, we should find normalized solutions for those four regions that have the right asymptotic behavior as you approach the singular point, 0 and infinity, from those sectors. And then there's potentially a mismatch that happens across this curve here, which we'll take just to be the unit circle in the plane. And this common intersection point, of course, that's the image of zeta equals 0. That's what that is. And these are plots in the lambda plane. Okay, so when we do the computation, we build these 4 solutions for the seed. What we find out is that actually there is no jump at all across the unit circle. So it's really a dotted curve here. There's nothing there. This matrix function psi actually only has jumps across the blue and the red curves. And we can compute those using connection formulas for Whittaker functions. So here at the end is what the Riemann-Hilbert problem looks like after we build in the Schlesinger transformations to increment these indices. I'll say something else about that later on in the D7 setting. So when n is equal to 0 in particular, the matrix will take off some power and an exponential factor, and we'll call this matrix Y. And it satisfies the following Riemann-Hilbert problem. So Y is going to be analytic in the complement of this contour, which is just the image of the real line for zeta. It takes continuous boundary values on either side. And then there are jump conditions. Y plus is Y minus times the matrix V. And the V is really 4 matrices because there are 4 pieces of this contour. There's 2 red parts, an arc that connects to infinity and 1 to 0, and likewise these 2 blue arcs like that. So correspondingly 4 jump matrices, and they're either upper or lower triangular, as you can see here. So they're really Stokes matrices for the problem. And then there's a normalization condition that the matrix Y tends to the identity as lambda goes to infinity, while Y times lambda to the minus m plus a half sigma 3, this is really theta 0 here, is bounded as lambda tends to the origin. And, we have to be rather careful with these power functions, so we're always choosing them to have a cut that's on the blue curves as it happens in the picture. One of the things that I wanted to point out here is that something interesting happens when m is a half of an integer, because you'll notice that there are these gamma functions with argument either plus 1/2 plus or minus m in the denominators of these off-diagonal elements. So that means that if m is a half integer, positive or negative half integer, then half of these jump matrices actually become trivial, and we end up with a triangular problem. And a triangular problem you can solve by some other techniques. It's sort of related to the Fokasitz-Kitaev problem. There's some orthogonality in the background. So that leads to some change actually in the behavior of the solutions when we have m being a half of an integer while n is an integer. Okay, so just to go into these Schlesinger transformations, if we want to generalize from the seed at n equals 0, we've got to apply these gauge transformations. And so if we assume, as we know to be true when n is 0, that psi times this power factor and the exponential has an asymptotic expansion at infinity with some coefficients psi infinity 1, 2, 3, and so on. And likewise at 0, it has an asymptotic expansion. Then we can simultaneously, for example, we could increment the theta 0 and the theta infinity. We could decrement that one by 1 at the same time. That's the same thing, by the way, as replacing n with n plus 1. And we're not really changing in any essential way the jump matrices. And the idea there is just to use a gauge transformation that involves lambda to the half and lambda to the minus 1/2. And it has a coefficient matrix b hat in it. And b hat is just built out of this matrix element, the elements of this matrix and the elements of this matrix here by some explicit formula. And there's a similar, actually it's the inverse Schlesinger transformation that has the opposite effect. It decrements the theta 0 and increments the theta infinity by 1. Okay, so that's decrementing the value of n. Okay, so then we can use this Riemann-Hilbert representation that now by the Schlesinger transformation, it holds for sort of arbitrary integer n and arbitrary complex m like that. And we can analyze this Riemann-Hilbert problem using the Dave-Joe method. And this is something that we did in a paper with Thomas Botner. So one thing is that when n is a large number, a large integer, and m is not a half integer, and we fix m to be a fixed non-half integer, then there's a certain domain that has the shape of a cat's eye or something like that. You can see it in this picture here. This is the eye that I'm talking about in the complex plane. So that domain is called E. And when x is in a scaled version of e by n like this, then this un function, it's approximated by a specific elliptic function depending on x, and it has a phase shift and an elliptic parameter that depend in a non-analytic fashion on the slow variable x over n, which is something that is sort of parameterizing this I-shaped domain like that. So you can kind of see it here. Maybe I'll zoom in on it so you can see a little bit better. So, so this is the I-shaped region here. This is the I, just like that. And then you've got poles and zeros. These are just plotted from the numerical, from some numerical procedures. So the blue dots, filled and unfilled, are zeros. Red dots are the poles of this thing. And it turns out because there are filled and unfilled dots, this is related to the fact that there are different factors, different polynomial factors in the numerator and denominator of these rational functions. Anyway, one of the things that comes out of the analysis is that it's possible to find sets of curves whose intersections are very close, asymptotically closer and closer as n increases to the locations of the zeros of any of these four factors. So here I just picked the ones that go, the curves that go with the unfilled blue dots. And so you can see that there's two sets of curves here, and where they cross is very close to these unfilled blue dots like that. Okay, so that's one of the results. And then, when x is in the exterior outside of this scaled I-shaped region, the u function is approximated instead by an analytic function of the slow variable x over n. And here, the approximations in these two types are really just non-equilibrium and equilibrium solutions of some approximating equation in the same way that we talked about for the D7 degeneration at the formal level anyway. And then when n is a large integer and we fix m now to be a half integer, that's kind of the unusual case somehow. So then it turns out that the equilibrium approximation that used to hold just outside of this I over here, it now extends inside of the I from one side or the other. And the only place where it's not valid is like one of these eyebrows, or maybe the other. That's what we call them, eyebrows. So for example, for one half integer value of m, the picture looks like this. So here, this is sort of zooming in on this dark curve is just the right eyebrow. And then you see that, okay, there's some finitely many curves that are attracting poles and zeros of the actual rational solution. The number of these curves sort of roughly parallel to the boundary is related to the size of this half integer value of m. Okay. So these are these are some results that come out of that Riemann-Hilbert analysis in the case of the rational solutions. All right. So now I want to go back to the D7. So let's recall, if we start out with this non-degenerate D6 version of Painlevé-III, we take gamma to be 0 to get down to the D7 form, and then we should assume that alpha times delta is not equal to 0. And as we said, to fix some connection with the literature, we're going to choose alpha to be 8 and delta to be -1 without any loss of generality by some scaling. So then there's a unique algebraic solution that has the behavior of 1/2 times x to the third plus small as x goes off to infinity for every single n. And that happens if and only if the beta is 2 times n. N is an integer here. It's a rational function of x to the 1/3, and we can write it if we want in terms of Oyama polynomials. So here I want to follow the steps of this Iso Monodrome method to characterize these functions and study them for large n and hopefully understand the bow ties. Okay, so if you look at the part 2 paper of Jimbo and Miwa, they write the lax pair for Painlevé-III D6. We already used it and written it on an earlier slide. So it's given in their paper with the normalization that gamma and minus delta are both equal to 4. Now you can scale to arbitrary non-zero values of gamma and delta by just changing the coordinates somehow, but you can't just set gamma equals 0 at the end of that process to get the lax pair for the D7 equation. And the reason for that is that in order to get D7 to come out as the compatibility condition of a lax pair, it's essential that the coefficient matrix of the most singular terms at lambda equals 0 is not diagonalizable. Well, you could take one or the other, 0 or infinity, but only one of them is diagonalizable, the other one is not. So here's a lax pair that you can find in a paper from 2004 of Kitaev and Vartanian. So here the matrix that used to be diagonalizable with eigenvalues plus or minus 1/2 Ix is now a matrix with trace and determinant both equal to 0. So this is a non-diagonalizable and non-invertible matrix. So this lax pair involves a constant parameter A, just right here on the diagonal in these two matrices here, and unknown functions P, Q, phi, and U of X. Okay. So if we write the compatibility condition down for this Kitaev-Vartanian lax pair, P and Q are just explicitly related to the other functions U and phi by some differential formulas like this. Then there's this equation that is a differential equation relating U and phi. And then finally, there's another equation that's a perfect derivative here that relates U and phi as well. So if we integrate the last equation here and we pick a concrete number for the integration constant, we'll take it to be I, right? Then we have this identity that relates U with phi prime. And then we can use this formula to eliminate phi prime from this equation here, right? We can eliminate these terms. And we're going to get a second order nonlinear equation for the function U, which is exactly the Painlevé-III D7 equation with beta equal to 2I times the parameter A that was in the lax pair. Okay, so for the seed solution, that was when n was 0. So beta is going to be 2n, which is 0. And the U function is 1/2 times x to the third. So if we take those nonlinear equations from compatibility in this situation, we can integrate and figure out what the other functions are. So the var phi function turns out to be 3i x to the 2/3 plus constant. And without loss of generality, again, by some gauging, we could take this this var phi 0 to be 0. And then the P and the Q, we can get them explicitly as well. Because they're coming from differentiation, so there's no ambiguity here. So that's P and Q, and you see that everywhere there's this e to the plus or minus 3 times x to the 2/3 showing up. So we could try to get rid of those by some gauge transformation. So it's convenient to do that. So we'll take them out with this exponential prefactor like that. So we're going from the matrix psi to some other matrix phi. So the lax system for phi, this is on the seed solution. The lax system for phi looks like this. So you see that, okay, now there's a much simpler and more obviously non-diagonalizable matrix that's on the sort of leading coefficient at 0. Okay, but pretty elementary coefficients. So we're going to be able to solve this problem. We're going to focus on this x equation because, well, we know what these things are as functions of x. So we're going to exploit that to try to solve this problem. And the first thing we might notice is there's, of course, a whole lot of similarity between these two things. And by some rescaling and mixing of the variables, we can actually eliminate completely this highest degree term. So let's do that. So we're going to set lambda to be capital lambda over capital X. So these are like new spectral and, independent variable coordinates, deformation coordinates. And little x is the same as big X. So then we write the Jacobian out and so on, and we get the partial derivatives with respect to big lambda and big X. And then in these new variables, we mix up things in the X equation, right? So that's what's happening here is we're taking this combination, which is cooked up exactly to kill those highest order terms as lambda. Now the capital lambda goes off to infinity. So now you see the X equation is a lot simpler. It has a constant term and a 1 over lambda term only. And in this transformation, we've retained this non-diagonalizable coefficient here. That's some simplification, actually, that we want to keep in the X equation. It means that there's actually not as much going on with this coefficient as ordinarily there might be. So anyway, so to deal with this, to simplify it further, and also to deal with these x to the 1/3 that are everywhere, let's now introduce z as x to the 1/3, and we'll make a constant gauge transformation to somehow simplify this matrix. So now omega will be the new unknown. It's linearly related to phi, and we have a new independent variable z. So what does this equation turn into? So it just turns into something off diagonal and with polynomial coefficients now in z. So it's really close to the area equation, actually, and just a few more manipulations finish the process. So anyway, so a fundamental matrix for this differential equation is, okay, omega naught of z with parameter lambda. So, okay, there's a diagonal matrix delta of lambda. It's just written here like this. And then there's f of xi. So here, xi is a combined variable that involves z squared and also lambda like this. And this f, this is just a fundamental matrix for Airy's differential equation in the variable xi. So f double prime minus xi f is equal to 0. So, okay, so the general solution then of this differential equation is, okay, this fundamental matrix multiplied on the right by something that only depends on lambda. So we'll call that h of lambda. Okay. All right, so now we go back to the other equation in the lax pair, the lambda equation. We want to figure out what this h of lambda is, and we exploit the compatibility. And when you do that, you find out that this h of lambda is a scalar, a lambda to the power 1/6 times some absolute constant matrix h naught. And you could, of course, absorb that into the choice of basis of Airy functions. So, okay, if we go back now to the original variables for the problem, the general simultaneous solution of the lax pair on the seed, okay, the seed is just this function 1/2 x to the third when beta is equal to 0, because n is 0. That's this function here. So psi of lambda x is the exponential gauge transformation we put in. Here is a constant matrix, and then we have a power x lambda to the 1/6 sigma 3 times this fundamental matrix for the Airy equation. And xi was related to the original variables now by this formula here. So somehow xi goes to infinity when lambda either goes to infinity or to 0. So that's what we have to watch out for. Okay. All right, so this general solution that we wrote down is branched at the origin, and it also has Stokes phenomenon in both limits. Lambda goes to 0 and infinity, because that's where xi goes to infinity, and infinity is the singular point for Airy. So it's easiest in this case. I'm going to do it in the simplest situation by specifying the asymptotics under the condition that x is a positive quantity. Remember, these Stokes sectors twist around in a complicated way as the argument of x moves. So I'm going to fix the argument of x to be 0, and then I get pictures that I can draw in a sort of simple way like this. So what happens is we can define 3 domains that have these simple boundaries. So this is the unit circle. There's an interior domain d naught, and then there are 2 exterior domains, d infinity minus and plus, like that. Okay, so if we're in either of these exterior domains, then we're going to use a basis of Airy functions, which one of the elements is just the Airy function itself. And then depending on which domain I'm in, I'm going to use one of these rotated Airy functions like that. And we pick the constants specifically to get good normalization at the point at infinity. So C1 plus or minus are these explicit numbers here. Actually, there is no dependence on the plus or minus, and C2 plus or minus are these numbers. And then if I'm in the interior domain in here, now I'm going to use the basis that has just the 2 rotated versions of Airy. So there's the forward rotation and the backward rotation with constants that you can see written here. Okay, so as I said, the purpose of those constants is to give us a nice normalization. Okay, so each of these 3 solutions is analytic in the indicated domain like that, and they have some normalization like this. So here at infinity, if we take psi and we multiply on the right by this exponential factor, then we have an asymptotic expansion in powers of negative powers of lambda, but it's convenient to lump that with x in this way. So I lambda over x to the minus p. So it starts off like the identity, and then we have this infinite asymptotic power series expansion. And then as lambda goes to 0, if we take the solution that's inside here, we again peel off an exponential factor, multiply by a constant eigenvector matrix, and then there's a fractional power of the same I lambda over x. That thing has an asymptotic expansion in now positive ascending powers of I lambda over x with coefficients bp of x. Okay, so that's just straight from the Airy functions. Now, because the 3 Airy functions add up to 0, because they're not independent, we can relate the solutions to each other. So in other words, we can compute the jumps across the boundaries of these curves. So that's some jump contours. So they have some notation here. So C plus and minus are the 2 pieces of the circle. And then we have sigma infinity plus minus, the parts that are unbounded. And there's also this sigma 0 plus that goes to the origin like that. So we take into account the jumps from this formula here, and we also have to take into account that the C variable has got a jump on this positive imaginary axis. So anyway, so then what we find is that psi plus is psi minus times V, and V is a piecewise constant matrix that's computed from all this calculation that I've described, and it's written here. So you can see there's 5 different constant matrices, all of which have unit determinant. Okay. So this matrix psi, it satisfies the conditions of a Riemann-Hilbert problem. And what we're going to do now is replace the index n equals 0 by an arbitrary integer. And what we're doing is we're using iterated Schlesinger transformations like we did for the D6 problem, but it's actually a little bit unusual how it affects the Riemann-Hilbert problem in the case of the D7 degeneration. It's a little bit weird, so I would like to show you what happens there. So first of all, the gauge transformation that you have to use, these are described in Kitaev-Vartanian. So for instance, if we want to map from n equals 0 to n equals 1, so then we're going to replace psi 0, which is the matrix that we've just built, with psi 1, which is some gauge transformed version of psi 0. And the gauge matrix looks like this. So it's built out of the coefficient at infinity and also the coefficient at 0 here. This is really the ratio of the second column entries of the coefficient at 0, the leading coefficient there, in our expansion of this psi 0 function. And so this mapping, it preserves analyticity in the 3 domains. It also leaves the jump invariant except on the branch cut, and there it just changes the sign of the jump. And so that's a trivial modification. Okay, so, but what does it do? What does this Schlesinger transformation do? It changes the asymptotic behavior at infinity. So before we just had this series expansion, and now we pick up this factor of I lambda over x to the sigma 3 on the right, just like that. And as lambda goes to 0, previously, I guess we just had this series here, but now we have it modified with this negative half power to sigma 3 of the same function, I lambda over x. So the point is that the power of I lambda over x to the sigma 3, it's increased by 1 at infinity, it's decreased by a half at 0. That's the effect of going from n equals 0 to n equals 1. And also the coefficients have changed. So now we have AP1 and BP1 like that. Okay, so that's going up 1. So the powers have gone up 1 there at infinity and down by a half at 0. Okay, so now we're going to apply that same transformation again to go from 1 to 2, because I have to show you the pattern. So that's this formula here. So it's the same matrix, actually. It's the same transformation matrix. It involves different coefficients. They're coming out of psi 1 now. And significantly, to get the potential that we need to show up in this matrix, now we have to take the ratio of the first column entries of the leading coefficient at 0. That's the consequence of the way we derive the differential equations from the lax pair. But in any case, to get out these necessary formulas for the potentials, we've got to switch the column for this B1. Okay, but anyway, again, analyticity is preserved in the 3 domains. V is invariant except on the branch cut where it changes sign, and so that means it's changed twice. So we're back to the original sign. So what's happening now at 0 and infinity? Okay, well, as lambda goes to infinity, we pick up a series with some coefficients AP2 and 2 copies now of I lambda over x to the sigma 3. So 2 times increasing by 1, we've increased by 2. That makes total sense to me. But if we look at what happened at 0, if we take this expansion at 0, now we're back to the situation where we just have this unmodified power series here without this minus 1/2 power to the sigma 3. So what it means is that the power at the origin has increased by a half, and consequently it's gone back to the original value. So whereas the exponent at infinity has increased twice in the same direction, the one at 0 went up and then it went back down again in the consequence of, or as a consequence of incrementing n 2 times. So anyway, if you follow that reasoning, you find out that this matrix W, that's psi times an exponential factor that normalizes things at both singular points, it solves the following Riemann-Hilbert problem. So W is analytic on the complement of those jump contours, and it's got it has a jump matrix V tilde, which is equal to V everywhere except on the branch cut, and it's equal to -1 to the n times V on the branch cut. And then we have just the conjugation by this by these exponential factors of v tilde for the jump relation. And then normalization, this is where it's kind of interesting. So as lambda goes to infinity, we pick up a factor here, I lambda over x to the 1/2 n sigma 3, like that. And then at the origin, what you'll notice is that the power flips back and forth. So -1 to the n is showing up on the right over here. Okay, so that's sort of an unusual Riemann-Hilbert representation. So it's somehow the Riemann-Hilbert problem looks different for even and odd values of the index n. And it's also true that when you extract the solution un of x from the Riemann-Hilbert problem, you've got to look at either the first, the second column or the first column of this coefficient matrix Bn. Okay, so then addressing argument shows us that this un function is a solution of the D7 equation when beta is 2 times n. And then we can derive a Becklin transformation from the Schlesinger transformation, and it preserves the algebraic character. So that means that this Riemann-Hilbert problem contains in it the unique rational solution of x to the 1/3 for the Painlevé-III D7 equation. Okay. All right. So I have just 4 minutes left, I think. So anyway, I would like to tell you a little bit about how we think about large n. It's useful to make a change of the variable to move the branch cut, actually, to make it go down instead of up. And when we do that, we end up with another matrix that's called y. And if we peel off the exponential factor for y, the constant jumps that it satisfies are a little bit simpler looking now on these contours. There's also an extra jump that shows up over here, just like that. Its jump is just plus or minus I sigma 1, so purely off diagonal. Okay. So I remind you that there was a kind of heuristic scaling that we made, something like x was n to the 3/2 times a parameter y. And based on that, we can also scale the spectral parameter in the problem. And when we do that, we can end up with an exponent. So this complicated looking exponent here comes out as just n times some phase capital phi of eta y, which looks like this. And so now what we do is we just take out a constant factor and we write z in terms of eta and y. So zn is the thing that I want to look at when n is large. And when we analyze this zn, what's useful to do is to introduce a g function. This is a typical tool in the Degeneration method. So it's a scalar function that maps eta. This is the new spectral variable to g of eta y. It's independent of n, and it's analytic in the complement of the jump contour. And the thing is that what we want is we want this function f, which is really the square of dg d eta minus d phi d eta. We want that to be continuous except at the origin, and that there's some g0 of y, so that when we expand the g out, we get a logarithmic term plus constant plus small at infinity. Okay. So we use this g to obtain a new unknown by some conjugation, and then we look at this m. Okay, so at this point, the spectral curve shows up, and so the idea is we need to consider this function f to be analytic everywhere except at the origin, and it's got an asymptotic expansion at 0 and infinity that we can work out by the conditions on g. So that's written here, and what this tells you is that up to this factor of minus I eta to the minus 3, this f is a polynomial. It's a polynomial of this form. So there it stands. It has an arbitrary constant in it that we cannot detect from the expansion. So that's really the spectral curve for the problem. And it's really related to the formal approximating equation. If we match the constant e to this parameter c in this way, then up to some scaling, the polynomial evaluated at y over 2u is exactly this thing that showed up in our proto-Weierstrass equation. Okay, I've got 1 minute left. So anyway, let me just say that the right assumption to make for large y is that you choose this constant c so that there's a double root. So genus 0 is what it means, really. So you have a genus 0 spectral curve. And so if you pick the right real root so that it has the asymptotic behavior minus y to the 2/3, then you've found the g function in closed form in this genus 0 setting. Here's the formula for it in terms of some logarithm. And now you think about what the effect is of putting this g function into the problem. That has something to do with the landscape of the real part of this function h. That's g minus the original exponent phi. And so here's just some plots of that and how it varies depending on y. So you see that, okay, if y is kind of big enough, then you have this picture where there are two curves that come out of this point. This is the simple root. Here's the double root of the polynomial. And on the other hand, when y decreases enough, there's a break that happens here. Okay, so that's really the thing that detects the edge of the bow tie, I would say. And since I'm out of time, I'm not going to describe it so much, but let me just tell you a theorem that we can prove from this. So this is a theorem that says that there's some number yc positive, so that if I look at this algebraic function as a function of the argument n to the 3/2 y, then that's going to be a square root of n times some capital U that solves this equilibrium cubic equation. Okay, and the error is of size n to the minus 1/2. So just some plots. This red curve is exactly that equilibrium cubic, and then you can see that these dotted curves, which are really the exact solutions for different values of n that are increasing, are hugging that red curve closer and closer as n increases. So that's the analytical solution, and analytical theorem. Let me just say that you can also rotate things now in the complex plane, and as such, you can detect the boundary of this bow tie quite accurately. So it's possible to find the boundary of the bow tie by looking at this function. So the real part of h evaluated at the double root should be 0. So let me just show you those pictures, okay? So here's the complex y plane now. Y is like x to the 1/3 rescaled. And so you see the Oyama zeros, and now this curve here, that's the bow tie theoretically, and it's just catching exactly those zeros very accurately. I want to say one more thing about it, which is that the boundary curve is sort of interesting. It's transcendental here and here, but these curves are exactly straight lines. Okay, well, that's it. So thank you very much for your attention.
Thanks, Peter, for your talk. Any questions, remarks? Okay, thank you. Thank you.
No problem.
And that ends our today meeting at the conference, and we meet tomorrow morning. Bye.
Bye, everybody.